Caproni Ca.60 Noviplano. In the years immediately following World War I, commercial aviation barely existed. Flying meant cramming into a converted military biplane made of wood and canvas, enduring a loud, freezing, and short trip between neighboring cities. But the aviation industry already had its eyes on a much larger prize, a regular passenger route across the Atlantic Ocean. To cross the Atlantic, an aircraft needed to carry a massive payload of fuel, along with enough passengers to make the transatlantic trip profitable. This created a brutal engineering bottleneck. The wooden fabric used in the 1920s could only support so much aerodynamic stress. If designers tried to build a longer wing to generate more lift, the wing would simply snap under its own mass. The materials of the era strictly dictated the physical limit of the machine. Italian aviation pioneer Gianni Caproni decided that if he could not build a longer wing, he would simply use more of them. On the shores of Lake Maggiore in 1921, Caproni unveiled the Caproni Ca.60 Noviplano. It was a flying boat of staggering proportions, designed to carry an unheard-of 100 passengers across the ocean. Gianni Caproni tried to solve the payload limit of the 1920s not by designing a better wing, but by aggressively multiplying the wings he already had. The aircraft was roughly 60 feet long and featured an astonishing 9 wings, arranged in 3 tandem sets of triplanes suspended over a central passenger hull. To power this floating lumberyard, Caproni attached 8 heavy V12 engines. The engineering logic was straightforward. Stack enough short, structurally sound wings together, and you can achieve the lift of a massive wingspan without the structural weakness. But the Caproni Ca.60 fell victim to aerodynamic realities that were poorly understood at the time. When wings are stacked closely together, they interfere with one another. The air rushing between the 9 wings and the thick web of bracing wires created a forest of turbulence and immense aerodynamic drag. The aircraft wasn't just generating lift, it was acting like a massive 60-foot parachute. On March 4, 1921, the Caproni Ca.60 took to the lake for its second test flight. As the engines roared and the massive craft accelerated, the crushing drag and unbalanced center of gravity took over. The aircraft pitched up too sharply, immediately lost what little lift it had, and slammed nose first back into the water. The wooden hull shattered upon impact, effectively ending the project, though the pilot miraculously survived. The brief life of the Caproni Ca.60 carried a harsh industrial lesson. Aviation scale could not be achieved by simply bolting more World War I parts together. To truly carry heavy payloads across oceans, the industry would have to abandon the multi-wing concept entirely, waiting instead for the advanced metallurgy that would finally allow the modern monoplane to take flight. Stipa-Caproni. In the early 1930s, aircraft designers faced a frustrating physical ceiling. For decades, the standard way to make a plane fly faster was simply to bolt a larger, more powerful engine onto the nose. But this brute force approach was yielding diminishing returns. An exposed propeller spinning in the open air is inherently inefficient because a significant amount of the air it pushes slips off the blade tips and disperses outward. Engineers couldn't just spin a propeller infinitely faster to compensate. Once the blade tips approached supersonic speeds, they lost their aerodynamic grip entirely. Italian engineer Luigi Stipa realized that the problem wasn't a lack of horsepower. The problem was that the propeller's energy was bleeding out in all directions. To fix it, he designed an aircraft that essentially swallowed its own propulsion system, the 1932 Stipa-Caproni. It looked like a flying barrel, but the Stipa-Caproni was actually a brilliant attempt to trap and focus the wasted energy of an airplane propeller. Instead of building a traditional, slender fuselage just to hold the pilot, Stipa constructed the entire body of the aircraft as a massive, hollow wooden tube. The engine and propeller were mounted deep inside the mouth of this tunnel. By wrapping the fuselage around the propeller, Stipa turned the entire airplane into a crude Venturi tube. When the propeller pulled air inside, the tapering barrel squeezed and accelerated that air, forcing it in a straight, concentrated column out the back. Instead of thrust slipping uselessly off the propeller tips, the enclosed duct focused all the available energy directly rearward, drastically increasing the engine's lifting efficiency. The concept worked exactly as the math predicted, but it immediately collided with the material limits of the era. While the ducted propeller was highly efficient, the massive, bulbous wooden tube required to house it created immense aerodynamic drag. During flight tests, the Stipa-Caproni lumbered through the sky at a top speed of just 81 miles per hour. As a practical aircraft, it was far too bulky to be useful. But as an industrial proof of concept, it was deeply visionary. The Stipa-Caproni proved that an airplane's fuselage did not just have to be a passive container for the pilot. It could actively compress and shape thrust. This awkward, barrel-shaped airplane successfully validated the ducted fan principle, planting the theoretical seed for a technology that would eventually bypass the open propeller entirely: the modern jet engine, Blohm Voss BV 141. During the early days of the Second World War, military reconnaissance crews faced a deadly physical constraint. They often couldn't see what was directly in front of them. In a standard single-engine aircraft, the engine block and the spinning propeller were mounted squarely on the nose, right in the pilot's line of sight. This created a massive structural blind spot, obscuring the ground targets they were supposed to map and hiding the approach of enemy fighters. The standard fix was to build a twin-engine plane, moving the engines out to the wings and leaving the nose clear for an unobstructed glass cockpit. But twin-engine planes consume double the precious fuel and aluminum, materials that a wartime economy could not afford to waste on observation aircraft. Aircraft designer Richard Vought realized the problem wasn't the single engine. The problem was the human assumption that airplanes had to be symmetrical. His answer was the Blohm and Voss BV 141. The Blohm and Voss BV 141 looks like a factory error, but its lopsided shape was a mathematically perfect solution to a deadly battlefield blind spot. Vought completely decoupled the crew from the engine. He placed a single engine, the long main wing, and the tail section on the left side of the aircraft. On the right side, he mounted a heavily glazed, greenhouse-like crew pod. By stripping the fuselage away from the propeller, the crew was granted an incredible, unobstructed 360-degree view of the battlefield below. To the human eye, an aircraft heavily weighted to one side looked completely incapable of flying straight. But the asymmetry was deeply intentional. In a conventional plane, a massive spinning propeller creates rotational torque, a twisting force that constantly tries to pull the aircraft off its heading. But in the BV 141, the heavy crew pod was placed off-center on the right wing. That dead weight naturally pressed down, perfectly counteracting the engine's twisting pull. The physics balanced automatically. Despite its bizarre silhouette, the BV 141 flew beautifully. German Air Force test pilots reported that it handled extremely well and easily met its tactical requirements. Roughly 20 prototypes were built, proving the off-center math worked perfectly in the sky. Yet, the military ultimately rejected the aircraft for mass production. The decision was driven partly by logistics and a lack of standard parts, but heavily influenced by an institutional reluctance to adopt an airplane that looked so obviously wrong. The BV 141 was a mechanical success defeated by human bias, remaining a striking reminder that aerodynamic symmetry is often just an aesthetic preference, not a strict law of physics. Vought V-173 Flying Pancake. Operating an aircraft carrier during World War II demanded an impossible aerodynamic compromise from engineers. To survive in combat, a fighter plane needed to fly fast, but fast planes require small, thin wings, and the fundamental problem with small wings is that they lose their aerodynamic lift the moment they slow down. This created terrifyingly high stall speeds, forcing pilots to slam their heavy fighters onto short, pitching wooden flight decks at deadly velocities. If designers tried to give the planes larger wings to let them approach the ship at a safe, slow speed, the extra drag ruined their top speed in a dogfight. Naval aviation was trapped in this lethal trade-off. Aeronautical engineer Charles Zimmermann realized that if he turned the entire airplane into one giant wing, he could solve the deadliest problem of naval aviation, the carrier landing. His answer was the Vought V-173, an experimental aircraft quickly nicknamed the Flying Pancake. Rather than attaching long, drag-heavy wings to a heavy cylindrical fuselage, Zimmermann designed a perfectly flat, disc-shaped lifting body. In this design, the fuselage itself was the primary aerodynamic surface. At the extreme front edges of this bright yellow disc, He mounted two massive propellers that spun in opposite directions. The brilliance of the machine was in how it manipulated airflow. The counter-rotating propellers blasted high-speed air directly over the entire surface of the flat fuselage. This meant the aircraft did not have to rely entirely on its forward momentum to generate lift. Even when the plane was barely moving forward, the intense artificial wind washing over the disc kept it firmly in the air, preventing the sudden loss of lift that causes standard wings to stall and drop out of the sky. The results were astonishing. Across roughly 190 test flights, the V-173 proved it was highly maneuverable and could maintain flight at an incredibly low stall speed of just 15 miles per hour. A pilot could practically hover the aircraft into a controlled carrier landing at the speed of a bicycle, a feat that traditional high-speed fighters couldn't even dream of attempting. The flying Pancake decoupled lift from traditional wing shapes, proving that a lifting body could master both the sky and the short-field runway. But it was a brilliant mechanical answer to a problem that was about to be erased by history. Just a few years later, the invention of the jet engine and the angled carrier deck gave the Navy all the speed and runway space it needed, leaving this ingenious yellow disc as a magnificent piston-era what-if, McDonnell XF-85 Goblin. At the dawn of the Cold War, the United States military introduced a new scale of strategic warfare with the B-36 Peacemaker. It was a massive nuclear bomber capable of striking targets continents away. But this incredible range created a lethal tactical gap. No existing fighter jet had the fuel capacity to escort the heavy bombers all the way to their targets and back. Once the fighters reached their fuel limit and turned for home, the slow-moving bombers would be left to fly deep into hostile territory completely defenseless against waves of Soviet interceptors. Mid-air refueling was still in its unreliable infancy, and strapping extra external fuel tanks to standard fighters simply wasn't enough. To protect its bombers over enemy territory, the United States Air Force built a fighter jet so small it could be stored in a bomb bay. But they forgot to account for the invisible wall of air beneath the mothership. The McDonnell XF-85 Goblin was designed as a parasitic fighter. Measuring just 15 feet in length, it looked more like a jet-propelled egg than a combat aircraft. It had no landing gear at all. Instead, it was equipped with folding wings and a retractable steel hook on its nose. The battle plan seemed perfect on paper. The Goblin would ride out the long journey safely tucked inside the belly of the B-36. If enemy planes appeared, the bomber would lower the tiny fighter into the airstream on a mechanical trapeze. The Goblin would drop away, fight off the interceptors, and then fly back beneath the bomber, perfectly hooking onto the trapeze to be hoisted inside for the ride home. But the neat mechanical plan was shredded by the violent fluid dynamics of mid-air wake turbulence. A massive aircraft like the B-36 displaces an immense amount of air, generating a churning, invisible wall of turbulent slipstream directly beneath its fuselage. When the tiny Goblin attempted to redock, it fundamentally lacked the physical mass and engine thrust to cut through that chaotic air predictably. During flight testing, the bomber's wake would catch the lightweight fighter and violently throw it upwards or sideways right at the moment of connection. Across 7 free flights, the Goblin managed only 3 successful dockings. The failure reached a terrifying climax when the turbulent air suddenly slammed the little jet upward, violently crashing it into the trapeze. The steel mechanism shattered test pilot Edwin Schaach's canopy and tore off his helmet, forcing a desperate emergency belly landing in the desert below. Schaach survived, but the Parasite fighter concept did not. The program was canceled when the military realized docking would be suicidal for average pilots in the stress of combat. The Goblin proved that mechanical cleverness cannot simply ignore atmospheric physics, ultimately forcing the Air Force to abandon the idea of planes hiding inside other planes and dedicate itself entirely to perfecting the modern mid-air refueling tanker. Avrocar Avrocar. During the 1950s, Cold War military planners stared at a terrifying logistical vulnerability. Jet fighters were becoming incredibly fast, but they required miles of pristine concrete runway to take off. In the event of a sudden nuclear strike, those static air bases would be the first targets. If the runways were bombed into craters, the entire interceptor fleet would be permanently grounded. The military desperately needed aircraft that could lift off vertically from any hidden forest clearing or shattered tarmac, and then transitioned to supersonic combat. Helicopters could manage the vertical takeoff, but their spinning rotors made them vastly too slow for high-speed dogfights. The Avrocar wasn't built to visit other planets. It was a desperate military attempt to build a fighter jet that didn't need a runway to fight World War III. Funded by the U.S. Army and Air Force, the Avro Canada VZ-9AV Avrocar was a genuine metal flying saucer. Instead of standard wings and rear-facing jet engines, it relied on a massive central turbine that blasted exhaust air outward. The air flowed over the craft's curved outer edges and pointed downward, utilizing the Coanda effect, a physical phenomenon where moving fluid naturally clings to a curved surface. This downward thrust trapped a high-pressure cushion of air between the saucer and the tarmac, allowing the heavy silver disc to lift off vertically. The hover mechanics worked perfectly, but the Avrocar was immediately crippled by a harsh aerodynamic reality. The trapped cushion of air, known as ground effect, only works very close to the Earth. As soon as the test pilot tried to climb higher than 3 feet off the ground, the air cushion dissipated, and the craft's center of aerodynamic pressure shifted violently. Because a perfect circle lacks the horizontal and vertical stabilizers found on the tail of a normal airplane, there was nothing to keep it flying straight once it left the ground cushion. Above 3 feet, the Avrocar began to suffer from a terrifying instability called hubcaping. It wobbled uncontrollably in the air like a spinning coin coming to rest on a table. The pilot had absolutely no mechanical leverage to stop the violent oscillation. Despite its supersonic ambitions, the wildly unstable disc never safely exceeded 35 miles per hour. The project was scrapped after millions of dollars were spent, effectively ending the military flying saucer dream. The Avrocar proved that exploiting ground effect for raw lift does not magically translate into stable, high-altitude flight, leaving the military with a machine that essentially acted as an accidental hovercraft instead of a revolutionary jet fighter. NASA M2F1 Flying Bathtub. Early spaceflight was defined by a terrifying, unsteerable fall. The first generations of spacecraft like the Mercury and Apollo capsules simply plummeted back to Earth like stones, suspended helplessly under giant parachutes. Because they could not steer, they had to aim for the vast target of the ocean, forcing the government to deploy massive, highly expensive naval fleets just to fish astronauts out of the water. The obvious solution was to give the spacecraft wings so it could glide to a conventional runway. But thin, delicate wings would instantly melt and tear off in the brutal, hypersonic heat of atmospheric re-entry. Spacecraft designers were trapped in a harsh physical compromise: a winged vehicle that burns up in the atmosphere, or a blunt vehicle that falls blindly into the sea. Before NASA could build the space shuttle, they had to prove they could land a spacecraft on a runway without wings. So they built a wooden bathtub and towed it behind a Pontiac. The NASA M2F1 was a scrappy, unpowered glider built largely out of plywood by a commercial sailplane manufacturer. It lacked traditional wings entirely. Instead, its fuselage was shaped like a thick, blunt half-cone. This was the lifting body concept. By simply angling the rounded belly of the heavy craft into the oncoming wind, air pressure naturally packed up tightly underneath it. This compressed air generated just enough aerodynamic lift to let the pilot control a steep, incredibly fast glide. It solved the spaceflight problem perfectly, a thick, blunt shape to survive the fire of re-entry, which could then use its own underside to glide home. To test if this blunt shape could actually be steered to a safe landing at low speeds, engineers didn't use a rocket. They hooked the bizarre wooden craft to a long tow rope, tied it to the back of a modified Pontiac convertible, and raced across the dry lake beds of California. The car had to hit an aggressive 120 miles per hour just to generate enough wind for the M2F1 to lift out of the dirt. But the scrappy test worked. Across more than 400 towed flights, test pilots proved they could drop the tow line, control the heavy glide, flare the wingless nose, and roll safely to a halt on a runway. The Flying Bathtub never went to space, but it remains one of the most vital, low-budget aerodynamic tests in history. It successfully bridged the gap between a falling capsule and a conventional airplane, providing the direct mathematical foundation that eventually allowed the space shuttle to return from orbit and land like an airliner. NASA 81 Oblique Wing Commercial and military jets flying at high speeds face an invisible, brutal wall of wave drag, requiring them to burn massive amounts of aviation fuel just to push through the air. Aircraft designers knew that a straight wing is perfectly safe for a slow takeoff but creates terrible drag at high speeds. Conversely, heavily swept wings slice through the air beautifully but perform dangerously poorly at low speeds. The military had already solved this compromise by building swing-wing planes like the F-14 Tomcat, which folded both wings backward in midair. But those heavy, twin mechanical hinges added immense weight, structural complexity, and maintenance costs to the aircraft. Aeronautical engineer Robert T. Jones envisioned a much lighter, radically different approach. NASA's AD-1 looks like its wing was installed backwards, but this bizarre pivoting design was a serious attempt to solve the brutal fuel costs of high-speed flight. Instead of two separate wings folding on two heavy hinges, the AD-1 featured a single, continuous wing mounted on one central pivot point. During takeoff, the wing sat perfectly straight, giving the pilot maximum lift and stability. But as the plane accelerated, the entire wing rotated diagonally. One side swept sharply forward, while the other side swept backward. By turning the wing to an extreme angle, the aircraft created a longer, much thinner aerodynamic profile. It effectively tricked the oncoming supersonic air into sliding smoothly over the wing rather than slamming directly into a flat leading edge. Between 1979 and 1982, NASA conducted 79 test flights, eventually rotating the solid wing to an extreme maximum sweep angle of 60 degrees. The physics worked perfectly. The oblique wing drastically reduced wave drag, proving it could theoretically double the fuel efficiency of a supersonic airliner compared to standard swept wings. But there was a catch. While the AD-1 was mathematically perfect for saving fuel, it was intensely disorienting for the human flying it. The asymmetrical shape caused extreme cross-coupling. If the pilot tried to pitch the nose up, the unbalanced aerodynamic forces would cause the aircraft to unexpectedly roll sideways. The project was eventually shelved, leaving behind a profound industrial lesson. Sometimes the absolute peak of aerodynamic efficiency creates a machine whose physics are simply too bizarre for a human pilot to comfortably control. Grumman X-29. Historically, airplanes were designed with an absolute safety rule. They had to be aerodynamically stable. If a pilot took their hands off the stick, the aircraft's natural shape would force it to return to straight and level flight. But in a fighter jet, aerodynamic stability is actually a physical limitation. A stable airplane naturally fights the pilot when they try to execute extreme, aggressive maneuvers. To build a more agile jet, engineers needed to make it fundamentally unstable. But traditional swept-back wings had a fatal flaw. During steep combat climbs, the air flowing over them pushes outward toward the edges, causing the wingtips, and the critical control flaps located there, to lose their grip on the air and stall. To break this agility limit, NASA and the military tested an aircraft that looked like it was flying backward. The Grumman X-29 was built so inherently unstable that human reflexes couldn't fly it. Its forward-swept wings forced the aerospace industry to hand over control to computers. By sweeping the wings forward into the oncoming wind, the X-29 completely reversed the normal flow of aerodynamics. Instead of sliding outward, the high-speed air was forced to flow inward toward the heavy fuselage. This meant that even when the jet was pulled into a violently steep climb, the wingtips remained fully bathed in fast-moving air. The pilot retained total control long after a normal fighter would have stalled and tumbled out of the sky. To prevent these backward-facing wings from bending upward and snapping clean off under the immense aerodynamic pressure, Grumman constructed them using advanced carbon fiber composites, rigid enough to hold their shape against the wind. But this radical geometry made the X-29 mathematically terrifying to fly. If the nose deviated even slightly from its flight path, the massive air pressure would try to violently flip the aircraft backwards. It would rip itself apart in fractions of a second, far faster than human nerves could process or correct. To survive, the X-29 relied on 3 redundant onboard flight computers. The pilot no longer pulled mechanical cables to physically move the flaps. Instead, the pilot moved the stick to ask the aircraft to turn, and the digital flight system fired out 40 microscopic control adjustments every single second just to keep the unstable jet pointing straight. While the striking forward-swept wings never became standard on mass-produced fighters, the invisible digital system inside the X-29 changed aviation forever. It proved that extreme maneuverability could be unlocked if humans trusted the math, marking the permanent transition from mechanical aviation to fly-by-wire computers. Rutan Voyager. Ever since the Wright brothers, aircraft range was dictated by a hard, unforgiving mathematical ratio: the structural weight of the plane versus the fuel it could carry. To fly further, an airplane needed more fuel, but holding more fuel required heavier aluminum tanks and stronger, thicker wings. That added weight created massive aerodynamic drag, which in turn burned more fuel. For decades, traditional metal airframes simply could not break this cycle. They were fundamentally too heavy to carry enough gas to circle the Earth without stopping. To break the ultimate limit of aviation, flying around the world without stopping, designer Burt Rutan didn't try to build a better engine. He built an aircraft that was practically entirely made of fuel. The result was the Rutan Voyager. Rolling onto the runway, it looked impossibly fragile. It was a bizarre, pencil-thin, twin-boom aircraft with wings so long and flexible they seemed guaranteed to snap. But its secret was in its materials. Rutan abandoned traditional aircraft aluminum entirely. Instead, the Voyager was constructed almost exclusively from paper-thin fiberglass, Kevlar, and carbon fiber composites. The empty airframe weighed less than a compact car. Because the structure itself was so incredibly light, almost every hollow space inside the bizarre shape, from the long wings to the twin booms, could act as a hidden fuel tank. When the Voyager finally took off in 1986, an astonishing 72% of the aircraft's total weight was purely fuel. It was so heavy that the tips of its massive, flexible wings literally scraped and dragged along the runway concrete as the plane struggled to climb into the sky. For the next 9 days, pilots Dick Rutan and Gina Yeager endured deafening engine noise and severe physical exhaustion, crammed into an unpressurized cockpit roughly the size of a bathtub. They successfully covered over 26,000 miles without stopping or refueling, touching down safely right back where they started. The grueling flight was more than just a human endurance record. The Voyager was a loud, highly public proof of concept for the future of aviation manufacturing. It proved that advanced carbon composites could completely rewrite the structural weight limits of an airplane, establishing the extreme material efficiency that now allows modern commercial airliners to cross the globe with unprecedented fuel economy.